My name is Ray Massey, and I am the Community Engagement Program Manager for AST's Power to Save. And it is my absolute pleasure to introduce you all to our presenters. So first, we'll start with Ms. Amy Silverstein. She's a 2-time heart recipient and a member of our Transplant Community Advisory Council. And then we have AST's past president, Dr. Ron Gill, professor of surgery and scientific director of the Transplant Research Center at the University of Colorado. Take the stage.
Thank you. Hello, everyone. Welcome to One Transplant for Life. How about that? One transplant that could last your entire life. It is a bold concept. And when I first heard about it last fall at an AST conference, it knocked my socks off. Because in my 30 years living with a transplanted heart, no doctor has ever dared to have the vision or the commitment or the courage, frankly, to make such an ambitious declaration that a transplant recipient could aim for, or dare I say, expect, that their transplanted organ would remain healthy and last for their whole lifetime. How amazing is that, right? Not just for transplant recipients, but also for donors, to think that their organ could live on and on. It is a sparkling idea and a brave goal. And you and I actually play a part in it. We have the power to save. You see, the reality of one transplant for life depends on us, the recipients. We need to have a say in this, a united voice, and an insistent voice, I think, because as transplant medicine stands right now, none of us, really, can expect that our transplants will last our whole lifetime. Our current medications and treatments are not going to get us there, and this is fact. And it is a fact that we all accept, and not at all begrudgingly, because we live day to day with enormous gratitude. We are the lucky ones, right? We receive donor organs, incredible gifts that saved our lives. We are filled to the brim with appreciation. So it would feel wrong for us, as phenomenally blessed transplant recipients, to say, I want more. I want a full lifespan with my transplanted heart or kidney or pancreas or liver or lung, what have you. It is our deep commitment to our donor organs that make wanting more feel uncomfortable. But I am here today to say, humbly but with conviction and passion, that we should want more. We should demand more of our doctors and the transplant research community and the powers that be at the NIH and HRSA that hold the financial strings that could make a huge difference in the research that bears on the length and quality of our transplant years. We should want more, yes, not just for ourselves and our families that love us, but also for donors. Donors, whether they're living or deceased, deserve to have their precious organs live on. Now, I know a donor mother who lost her teenage daughter tragically and donated all of her organs and saved many lives, and that was just 4 years ago. And already, the liver recipient and the lung recipient have passed away due to graft failure, and that donor mother is devastated. Now, I would love to tell her that her daughter's kidney and heart will live 50 years. They're young organs, after all, but I can't tell her this. It is not the reality in transplantation right now. So here's the thing. It is up to us, we transplant recipients, to move away from silence and acceptance on the status quo in transplant medicine and use our powerful voices for change. And change begins with opening our eyes and our minds to the incredible but also realistic goal of one transplant for life. And with that idea in mind, I turn this over to Ron Gill, who will lead the way forward. Thank you.
Thanks, Amy. Can you hear me okay? First thing I want to do is I want to thank CSL Behring for their support for this. I really appreciate their generosity, and it's been interesting in the process of these things how we can partner with our industry collaborators and how much actually they unfortunately, we talk about the big bad drug companies. Some of these people, it's important, we don't actually know who they really are. When you meet these people, you realize this ain't so. And I just want to thank you. And if this is terrible, you can blame them. And what this is the first of a series of presentations we're doing on behalf of the American Transplant Society of, whoever we are, the American Society, AST, American Society of Transplant. I should know, I was just the president of this society. So, and it's interesting, those of you who don't know who we are, we're actually the largest professional organization in the country. We have over 3,800 members and encompass all areas of research. I'm actually a research scientist, but clinicians and surgeons and nephrologists and pharmacists and public health and et cetera. And yet you would not know who we are. We have members in every transplant center in the United States. And we made a decision a little over a year ago to kind of reverse the trajectory from being just a professional society, seeing the gap in advocacy and partnership with the actual transplant community, and actually turn the mirror around and actually begin to engage you all. I heard one of our past presidents say, well, we speak on behalf of patients. And I said, well, when's the last time a patient actually spoke with us at all? And we actually with them, et cetera, et cetera. So this is our first attempt to actually, our first year to try to do that and become an organization that also involves the public. So we're delighted that you can be here. And if other questions, we have our booth over here. The Power to Save is kind of our public-facing slogan, if you will. And so we have a lot of people over here. We'll all be there, and we have a lot of staff people here. So welcome to this. There are two parts of what I want to talk about. So my task here is to talk about what is the research that's going on in this field. One thing is we need more of it, but that's a different discussion when we talk about advocacy and so on. But at least give it a sense of where things are. And I think one of the things that came up when we had our first ever summit last October in Washington, D.C., and asking what are the areas that people care about? One is education, like what is going on? What's a trustworthy source to find out about what's happening in this field, about advocacy, about finances and so on and so forth, and which is the core of what we'll be talking about. What I want to do is talking about research. And I want to emphasize something that's very important. We hear so much, even the opening ceremonies last night, about donation. And I think there's nothing to distract or dilute the message that donation is what gets everything on the board. And basically we need donors. But the other half I want to talk about is the other side. I think Amy was kind of referring to this, is what happens after. And I think that's the part, especially in the public eye, is missing. So yes, it's donation. Yes, the gift of life, the miracle of a transplant can never be underestimated, but it's not the whole story. And that's where I want to go in the next few minutes. So when we talk about research, a lot of times we say we want a cure, we want research. I've seen this in other disease conditions. It's important to begin to become specific. Well, what do you mean by that? And what actually is happening and where might we go? So there are two things. On the donation end, it's this one. This was actually a phrase coined by, we had our board retreat just a few days ago, and one of our board members blurted this out, is an organ, the one trans for life is the slogan for Power to Save. They said, but on the donation side, we want one transplant for all who need it. And that has to be our goal, is that everyone who needs something has access to a suitable organ. And the other half is afterwards, after that gift, after acquiring that organ, we want that, our goal, we talked about strategic planning in our society about 8 years ago. We're saying we want to increase graft outcomes by 5 years. And I never could get my head around what I wanted to say, and I blurted something out at our summit, say, no, our goal has to be one transplant for life, right? It's not a few years, that our mission is not better, our mission is indefinite, is going the distance with this. So when we talk about research, it's important to know what research actually is. Because we think it's like, well, some people sit in a room somewhere, and whoever they are, if you have their phone number, let me know, because I don't know who they are. Okay, but they sit around, they cook up something, and then all of a sudden we have a clinical application of something. And that's just not how it works. It starts, if you think of transplant injury as being the fire that we're trying to put out, how does that actually happen? And the first part is actually basic scientists, like the nerdy basic scientists at the top there. That would be me. Basic discovery. Give you just one quick example. How many of you have heard of cyclosporin? Okay, hopefully most of you. There will be an exam. So cyclosporin was actually derived people studying fungi in Scandinavia and finding that these fungi make these weird molecules. They're called macrolides, but they make these weird molecules to keep other fungi from growing in their area. It turns out, just by chance, when you study these molecules, they have these weird effects on immune cells. And that actually, one thing led to another over a series of discoveries. So first there's the basic discovery, like a fungus, Sirolimus. How many of you heard of that? Sirolimus, the name of that is Rapamycin, because it was discovered by the fungus on the island of Rapa Nui in the Easter Islands. Another of these weird fungal products, molecules that who knew, has these immune suppressive properties. And then the task over time is then take that and translate it through research for animal studies, other kinds of things, to find out what is the chance this can actually be applied to therapeutics, and then ultimately we have patient treatment. And so that is not always a linear process. Sometimes it takes weird turns and whatever, but what it is but as a larger group, is to look at the landscape. What is actually in development? What are the kinds of molecules and pathways and treatments that we can look at that can work its way up the food chain, if you will, ultimately to application? Because that's patient treatment is what we really want. But again, realizing that there's a path to getting there. So I talk about I'm just going to give you a few sound bites of the kind of research that's going on. What's the research that's aimed towards this one transplant for all in need? Well, one, of course, is public education. So if I were emperor, I'd put everyone in a headlock until they sign their donor card, but I'm not, and that's probably not how we should do things. So obviously getting more public donation and living donation is a huge area, and that's more public awareness, education, and so on. But there's also a science, a research in other areas that can increase acquisition to a donor. And I don't have a crystal ball on which of these will be best, but I'll tell you the three areas that are going on, and it's these three: organ preservation and resuscitation. I'll give you an example of that. One that you probably hear a lot about is xenotransplantation. That I'm actually an immunologist by training, so I study things that control the immune system. I've actually studied the immune response to xenotransplants, like when you're confronted with an organ from a different species, how does the immune system actually respond to that? Because the immune system actually gets very confused. And the third one I want to touch on is also stem cell technology. And if I were going to bet, and again, I broke my crystal ball long ago, but if I were going to bet that this is probably the rough order of sequence in terms of timeline, early, intermediate, and maybe later, what might hit clinical use, and maybe all three of these. The one that's obvious, I think, is basically organ preservation. And one thing you know that we have actually a fairly narrow criteria for what we use, like brain dead donors. But there are a lot of donors that are non-heart beating. How many of you have heard of like DCD? Anything? Does that ring a bell? Okay, at least a couple of you. Deceased after cardiac death for deceased donors. And of course, every time we get a donor, that organ is in trouble, right? It doesn't have a blood flow. It is under duress. Even a living donor, as soon as you take a donor out and stop blood flow, there's damage and injury that happens to that transplant. And so there are a lot of programs, and this is actually catching a lot of momentum to actually work on technologies and compounds, actually therapies that you treat the donor organ with even before you implant it into the recipient. And again, I don't have time to go into it. You can ask questions later if you'd like, or now or later. But organ preservation is a huge area, and actually to resuscitate. There are things, as we understand how tissues get hurt, how blood vessels get injured, we have a lot of compounds and things to actually, the technical term is secret sauce, that you use to infuse the donor organ to actually preserve its activity. And I just want to highlight this one. This has been transformative in the lung transplant field, and I think is headed to be a standard of care. If those of you are Star Trek fans, I realize it looks like Mr. Spock's brain, if you remember that episode. But in the University of Toronto, they found actually a way of preserving and revitalizing lungs. And actually, what you can do in this kind of a system is actually test the function and viability of the organ, and make sure it's going to be okay even before you implant it. So there's a huge area of research just going in organ and tissue repair and regeneration. And this, of course, the net result, it will expand the donor pool. It'll increase access to transplant. Another one is xenotransplantation. And when we call a transplant from another person an allograft. Allo means across, members of the same species, it means other, whereas xeno means across. So xeno means a transplant from a different species. And for a lot of reasons in terms of physiology and access, the pig has actually been the donor of choice, and probably the closest term thing that I could see xenotransplantation would be the area of diabetes, of pancreatic islet implantation as a source of insulin-producing cells, because there are reasons why these cellular transplants are easier than the organs. But nevertheless, it presents a fantastically huge resource for getting donors. But xenotransplantation is more than just supply, it's also design. And some of you may know that there actually is the ability to genetically engineer pigs so that they become more and more compatible and accessible to the human system. Because there are a lot of things when you go across species, there are incompatibilities that are important that can become a barrier. And there are now groups, there are actually companies that are making engineered pigs in a lot of different things where you can actually modify 8 different genes in the same animal to make it more and more suitable. And this, I'll refer to this as immunologists, this is the alphabet soup that we work with. No, there's not going to be a test on what these things are, but there are examples of all kinds of things that are emerging where you can genetically modify pigs to create a more and more human accessible and human compatible tissue. So there's a lot of hope there, and actually on the lower right there are these weird viruses that can be in pigs. Groups have been able to go in and genetically edit all of them out, which is an astounding research thing. The other thing is stem cells, and I start here. I've actually, especially in the diabetes world, I've talked to a lot of patient groups, and the one thing, our mantra is, if nothing else, tell the stinking truth, okay? And not pull on purse strings. Like, if you ask me how long will be that, I'll give you a blanket answer is I can't predict the unknown, and I can't be sure. Is it months? Is it years? Could it be decades? I mean, we have to be honest. The timeline of this is unknown, okay? And there's an area, stem cells, because I work in this area in bone marrow stem cells and other areas as well. Basically anything that will help a transplant do well. And the trouble with this field from a public perception is how much snake oil salesman stuff there has been out there. And this is actually a clip. This is from a 60 Minutes, this headline of a stem cell company that was basically just doing a lot of fraudulent stuff. And what happens is you can only play that card and cry wolf so much before you begin to jade the perception of the community, right? And what's real and what isn't. And what I can tell you is there's been a lot of stuff of just unreputable stuff out there, but there is a real thing that's going on in the stem cell world. And so first of all, what is a stem cell? A stem cell is a cell that it's immature and has the capacity to be coaxed to developing, I kind of think of it as like cellular alchemy, that you can take a cell and coax it to become different kinds of tissues, okay? And what that is, it's tremendously complex. I mean, our control of what becomes a kidney or a liver or a heart cell or a skin cell is very complex, and our biology works very hard for that to not change. Because when cells take a bad direction and go backwards in their development, what do we call that usually? Cancer, right? So we have a lot of safeguards that keep cells from doing that easily. But there was a breakthrough that the 2012 Nobel Prize in Medicine actually went to these 2 investigators who were able to work out a concept where you can take adult cells and kind of reprogram them. That term on the right there, that IPS, is an induced pluripotent stem cell. That name's not important for the moment, but the idea that you can take these kinds of adult cells and re-engineer them to become other kinds of tissues. Now, for clinical application, we're still a long way from the finish line. Just understanding how to do that safely. What keeps the cell from derailing when you try to redirect it into something else. There's an entire research world in there, and one that's getting actually a bit closer. And I'm skeptical. My wife teases me. I said I'm a sober optimist, or I'm a pessimistic hopeful person or something. Because, because again, you want to make sure that we're matching reality with what's actually going on. That's essential for us. But the fact that these things, like I said, the closest one is probably in the diabetes world, that generate insulin-producing cells from these kinds of stem cells. And once you have the technology, you can begin to coax these cells in different conditions in all kinds of tissues. What I can tell you, the idea, well, they're just growing kidneys in a dish, they're growing this and that is overstating reality. Are we on a track? I don't know what's in the future, but I can look in the rearview mirror and say that the ability to do this and move these kind of uncommitted stem cell-like things into differentiated or into new kinds of tissues is on the horizon, but it's a complicated process that's not ready yet. Okay, that's probably the best I can tell you in a soundbite right here. Now, but those are probably the three areas where affecting the donor has come into play. The one that is really my heart as of today is this one, is moving after transplant. The public understands, I'm going to go right here. I used this at our summit last year. How many of you have seen this movie? A few of you, several of you. For those of you who haven't, Return to Me is actually a fun movie. We own it. My wife and I own it. I've watched it multiple times. It really is fun. I love the minor characters in it. But Minnie Driver receives a heart from his wife who was killed in a car accident. And they meet and they develop a romantic relationship, him not knowing that he has his dead wife's heart. And it's a really fun story. But I think what it does is it misses a key message. Because in that movie, if you've seen it, everything's about her getting the organ. And she's terrible, she's deathly ill at the beginning. I understand that, that's all fair. She gets the transplant, and basically then everything's hunky-dory. She's self-conscious about the scar. They show her in a doctor's office, hey, it's all great, see you, Minnie. Well, that wasn't her name in the movie, but and what it misses is the fact is not understanding what life is actually like after transplant. And we want to make this as good as we can. We work very hard as a field. There are people in the audience from our society that they work fantastically hard at treating after transplant. But that message is not reality, right? And it's not about throwing out doom and gloom and fear, but realizing that we're not where we need to be as a field yet, okay? This was actually, what actually got me going in the patient initiatives. I've trained a lot of clinicians in basic science, and one was the director of our pediatric heart transplant program in University of Colorado, and he came in despondent and plopped down my office. And this is, like I said, this poster was, we used this a couple years ago at our Congress, and the issue isn't just to be melodramatic. This actual picture was patterned something I brought up from one of his patients, a little girl who got transplanted a year and a half with hypoplastic left heart, if some of you know what that is, a congenital heart defect, got a heart transplant. Things went great for a while, then things began to go south, and at age 8, had uncontrolled rejection and died. And I feel like this is where, I want to see those kids go to high school and college and beyond. Okay, and that's actually what's evolved in this message of one transplant for life, and that this is a tough thing to manage. Okay, and at the core of this is hidden in plain sight, and you all get this, but again, it bears repeating. The weird thing about transplant, and you might be kidney disease and liver and heart and diabetes and you name what the condition is, and lung and so on. We have one source of end-stage organ failure, right? And the miracle of transplant, the gift of life comes in as a transplant, but then what we do is we transition to a second condition, the condition of immune suppression, right? That managing this, and what are we dealing with? Drug-related toxicities, it says here. It affects our immune system. I'm biased, I feel like the biological universe revolves around the immune system because I'm an immune narcissist, okay? But you're trying to block a system that is really good at what it does. Our immune system is actually very talented in protecting us. Unfortunately, it doesn't know that kidney, or that heart, and that liver is supposed to be there, right? It just sees it as something that's foreign. And then that results in gradual graft injury. And so the key issues when you talk about after transplant is 1 year survival In the 1980s and early 90s, in the early days of cyclosporin, we were measuring success was 1 year graft survival, okay? And that's great. And we were happy when we hit like 50% 1 year graft survival. And unfortunately, a lot of the ways that we're measured today are still at that paradigm. And my question is, that's great. To make it to 30 years, you have to make it past 1. But do you really want to say you've succeeded when you transplant a 3-year-old and say, well, they might make it to age 4? If that's our end game, then it's like, count me out. I think all of you as well. And this is the issue: is long-term transplant outcomes have not changed in the last 2 to 3 decades. So we've hit kind of a steady state. We're much better than we were, but we're not where we need to go. And related to that, and this has to do with research and research funding and everything else, there's been limited innovation of what we're actually using in transplant. And this is the deal, is we're fighting the immunological Alamo, okay? We put up a valiant fight, except that the foe is just relentless and eventually wears you down. And the harsh reality of it, and it's just the truth, is that balancing keeping your immune system healthy enough to protect you and keeping the transplant going is a very fine edge. And gradually what happens in much too much of the time is the immune system gradually wears down and causes what we call chronic or long-term graft injury. And this is the paradigm I think we need to change, because most of our drugs, face it, don't redirect the immune system, they just blunt it. It's just blocking the immune system rather than modifying it. And I would say there comes a point, it's like curing a headache by cutting off the head, and that's never a good solution. And this is where I have a lot of work. I work also in type 1 diabetes. Our needle of expectation and looking in the horizon, and actually Amy touched on this in the very beginning, is like the early days of insulin therapy. It's just like organ failure. In the 1920s, insulin was discovered only in the mid-1920s. And back then, if you had if you developed new onset juvenile autoimmune diabetes, your life expectancy was weeks to months most of the time. And that's like, if there's no other alternative, end-stage organ failure, that's heading towards a cliff, right? And after the discovery of insulin, this is actually the life expectancy after giving insulin therapy over the decades. And it went from, early on, for the first several years, this is the 20s and 30s and 40s, life expectancy moved upwards of 30, 35 years, which at the time, as compared to the alternative, was fantastic. But if that's where we stopped, if you imagine if in the type 1 diabetes field, if life expectancy was only 15 to 20 years after having disease, we would consider that an incredible failure in the diabetes world. Now, type 1 diabetics are getting closer and closer to the national average in life expectancy because of incredible investment in research to modify that disease. And I would say that was, that's pre-World War II. We're in 2018. I think that our spectrum and our moving that needle of expectation has to radically change. This is interesting. On the juvenile diabetes research side, this is in their current website. Insulin is not a cure. It's a treatment, it's an essential treatment, but it's not a cure. And I kind of made up, and you think in disease, with this chart, I have to show some data because I'm a nerdy scientist, but it's interesting, the number of transplant patients last year exceeded the number of new onset type 1 diabetics in our country. But from a public perception point of view, you'd never know that. And so I would say, okay, let's take that, let's hijack that and say immune suppression is not a cure. It's a treatment. It is the best thing we have available today, but is not our future and not our horizon. Looking forward, just tweaking the same medications in the same way is not going to get us where we want to go. And so what I conclude with is just the sound, what is it, if it's not that, then what is it? Whoops, that's in my immunology lesson. In something called immune tolerance. And this is something that's not just in transplantation, it's in other areas like autoimmune disease and others where we want to modify the immune system. And there's a big paradigm shift that our care does not reflect the changes in what's happened in our perception of how the immune system works. Because the immune system is our friend and also our foe in this, right? Because we're trying to battle the immune system gets marshaled. Like I said, the immune system is, when the immune system locks on target, it is really good at what it does. And a real dilemma in immune-mediated disease is how do you calm down and redirect the immune system? And the really hopeful thing in studying immune tolerance, I'm biased because it's a big part of what I do. The reason this alphabet soup slide is on here is because immune cells, we think of, well, the immune system just kind of turns on and does stuff. But in fact, the immune system operates a lot like the nervous system. It has memory, it responds, sometimes it doesn't respond. In fact, why do you get vaccinated? You're getting vaccinated, you're teaching your immune system, you're exposing your immune system integrates all that information, looks at it and says, okay, the next time you see that, then it's poised to respond efficiently. The immune system has learned and developed memory over, like the polio vaccine. Your immune system remembers forever about polio without ever having to see polio. So it's actually good at learning. The good thing is, and the reason all these weird things are put up here, is because it's like the nervous system. It can turn up, it can also turn down. The immune system is, you can consider these kind of things on the surface of immune cells, these white cells, as the control panel. And some of them are designed to turn on, but others are designed to turn off. And we have all kinds of new emerging therapies and agents that actually can, instead of just blocking the immune system, to re-educate and retrain the immune system. And we have ways of actually, especially experimentally today, to do this. This is actually done in our own lab, but it's representative of many labs across the country. That's a transplant. In this case, it's either an islet cell transplant or a heart transplant. And if you put a tissue from one donor into another recipient that's different, like a typical transplant, and don't do anything, those grafts acutely reject because you activate the immune system and boom. But this is a case where we're giving 4 shots of an agent that's directed against one of those control structures, those control panel things on immune cells that can redirect the response. Just 4 treatments for up to 9 days. Most of those transplants will go forever, and these animals will actually literally die of old age with a transplant, a foreign transplant, without any other drugs for the rest of their life. And some of these concepts have moved themselves all the way up into non-human primate trials, and these things are actually merging. So we have a lot of tools that we don't yet know how to fully use and move into clinical application. But what we're finding is the immune system can be retrained. It doesn't just have to be poisoned, okay? And one example of that, how many of you have heard of belotasib? Okay, more than I actually might have expected. Belotasib is one of these kinds, the reason I highlight this, it's one of the new generation of agents that actually targets one of those control panel molecules that actually helps to redirect the immune system. So some of these are beginning to slowly find their way into clinical application. And whether or not this is the answer or part of the answer in the future, along with other things, I think we're going to need combinations of things that keep this from happening, promote that happening, because the immune system is complicated. There's no getting around that. But the fact that some of these agents that are they're more like smart bombs instead of just big bombs, they're more surgical and precise in how they actually affect the immune system. So I'm optimistic. Timeline, again, like I said, my shattered crystal balls in the back here. But the fact that we're moving in a trajectory as a field in this direction, I think, is very hopeful. And of course, the thing is here, I put this in that, why can't we do this tomorrow? Because we have to balance between safety and what is effective. A multivitamin would be really safe. It's probably not really good at blocking rejection, I'm sorry to say. But there are other things like you can lethally irradiate, like for bone marrow transplant, you can irradiate someone and completely destroy their immune system. No, they won't reject their transplant, but the collateral damage is not exactly what you'd like. So moving the needle from what it become more and more safe and more effective is the challenge that we're facing, is why this actually takes time to move these concepts to clinical use. And all of this is we want, again, our mantra is move towards one transplant for life and not just do a little bit better in the long term, okay? I'll stop there. Thanks.
Thank you.
So if anybody has questions, or again, you can always come over and visit us next door.
So
Yes, sir.
I have one. I'm a double lung recipient, and just 2 weeks ago, I started on belatacept because the cyclosporin has attacked my kidneys, and as a result, I'm now on dialysis. So they told me that if my kidneys come back, I'm still acute. They haven't made me chronic yet, that I could actually get off of dialysis. But, and I realized from your slide, and I've heard that this is a relatively new anti-rejection drug. Are we looking at long-term impacts of belatacept, or?
Yeah, potentially. That I can't answer that precisely. Um, so, like, will belatacept induce immune tolerance, the ability to stop giving everything, including the belatacept? As of today, probably not. We've learned, you know, it's like Edison. We're learning a lot of what not to do, and the things and like in my own research, like many of my colleagues, is okay. In very simple animal models, we can show this agent works, but then what are the things that complicate it, like diseases, like autoimmune disease and other kinds of things? What are the things that get in the way and keep that from inducing the same kind of protective immune response, this tolerance thing that we're looking for? But that's why I mentioned about belatacept being maybe not a tolerogen, inducing tolerance, but it's tolerance friendly. It helps create an environment in our immune system that we can then add things and ratchet up other things towards tolerance and get away from the toxicity of some of our current drugs. And we're caught but we're in between here and there, and that's the tension, right? It's frustrating for me. I'm getting more impatient. There were a couple of questions over here, right here, and then I know there's one over there as well.
I was transplanted at New York Presbyterian Columbia in Manhattan, and the NIH just took one person, did a study on, I had liver 13 years, so the guy's 75. They weaned him off of immunosuppressants, and for 6 to 8 months, at 75, and the liver goes 150 years, right? So the guy, he came back. It didn't work. So do you know anything about this NIH study about weaning people off?
Yeah, there are a lot of studies where we're trying to understand, like, who are people who do well. Like, you hear about someone who's 35 years out. Unfortunately, no, for every person like that, there's a person that their story is very different. And trying to understand what's the difference between people whose grafts do very well, and in fact, we can do more profiling, as it's called, immune profiling. It's saying what characteristics, what is the features of their immune system that actually distinguishes them from somebody else. And sometimes you have these sporadic cases where someone has for whatever reason, has come off all medications and they don't reject. I want to put word of caution there. That is a very dangerous thing to think about, because what is missing there, that makes Russian roulette look like a sure thing. I said yesterday to somebody that the denominator, the people who don't do well, is huge. And so I have to say that is a risk not worth taking. But begin to understand, and even to say, who are the people who have actually changed their immune profile, where they actually don't need the drugs and we don't even know it. So that's the kind of research we're talking about. I know it's called the Immune Tolerance Network and some of the others, those kind of NIH studies. So I've been on the committee for those things. So I actually know a lot about them, and where liver is probably the one, this drug weaning concept. Gosh, because the liver is a weird organ. It's massive. It does a lot of weird things that affect the immune system. And so to say that gently, this concept of weaning the medications, but you have to be ready. But I would always do that with a study, because if that begins to go in a bad direction, you want to make sure you lock that back in again. Yeah, you're saying blood work every week, because you want to stay ahead of that curve. The things are beginning to go in a bad direction. You want to know that really quickly. Sir.
Yeah, I have a question. I've been in transplantation since 1969 with Dr. Kuntz in Belzer, and I'm seeing more and more research on marijuana and how it can be used as a immunosuppressive medication. Any thoughts on that?
Well, yeah. That's a tough one because remember, remember the marijuana is still illegal federally. So you could never get federal funding to look at that, not in today's world, or at least there'd be big barriers to it. I don't think there's any evidence that marijuana is immune suppressive, okay? And the trouble is there's a lot of that we just don't know about. And coming from Colorado, we should be doing those types of noise. And Washington and a few other states. So yeah, I mean, that's a question that actually comes up a lot, but we're still very, both in terms of research and politics and everything else, we're in a very sensitive area on that one. Anything else?
Just a comment, actually, as the father of a 5-year-old little girl with a heart transplant.
Yes.
I just want to say thank you for your commitment, dedication to changing her future, and I know it takes a village, but you're a big part of it. So thank you on behalf of her and everyone here.
That's good to hear.
Yeah,
Thank you. Appreciate that.